Hi, my name is Jim Heffron. This sequence of videos are my Calculus 1 lectures. Just as with a textbook, a sequence like this should begin with some kind of description of coverage and approach and level so that somebody can decide whether this suits them. So we're going to do that today. And if you decide to stick around, if you decide that it does suit you, then at the end we'll do a little bit of talking about the history of the subject, just because that's a good first day topic. A lot of times people haven't got the book yet, aren't really settled in, so it's good to start off with something that doesn't really require too much in the way of notes. Okay, let's start in. So let's see. We will, in this sequence of lectures, cover the standard material of a U.S. College or University Calculus 1. As a person who teaches mathematics, I know that that how you approach the subject falls on a spectrum. Some students really need you to cover all of the algebra, some step by step. Some students are really sort of way ahead and are very mathematically mature and are looking to do quite advanced material in the first course. If you are somewhere in the middle, if you think you are somewhere in that sort of middle 85%, then this course is pretty much targeted at you. This is the standard thing that you would probably have if you went to, say, a large U.S. state university or a kind of a mainline U.S. college. It's going to be based on a standard textbook. The textbook is by Stewart, Clegg, and Watson, the 9th edition. But really, any popular text will probably fit the order of the material and the sort of level of difficulty of the material pretty well. I said they're 9th edition just to say, but I think you should notice that that if you use a different edition there, 9th edition, if you use a different edition, 8th edition, 7th edition, that you find online probably fits also. That is to say, if you can buy an edition that's a little cheaper, that might work for you. So again, before I go on to the next topic, if let's say you're a high school senior who's looking to get ahead a little bit in their fall semester college work, or maybe you had a little trouble the first time you took Calculus 1 in college and you dropped out and you're looking to sign up for it again in the spring, then this is probably this sequence of videos probably the right coverage for you, probably exactly what you're looking for. Okay, an approach. Again, not to say the same thing 5 times, but the approach here will be usual of a U.S. college or university calculus for science and engineering. That's as distinct from calculus for business, calculus for psychology, that kind of course. So science and engineering course, and again, we're trying to locate what's the right level for you. The lectures that I'm going to do, the videos that I'm going to do are something like 40 minutes, maybe 30 minutes. And in between, I'm going to do homeworks that are, they vary a little more, 20 minutes, 25 minutes, 30 minutes kind of thing. These slides, I like to use slides. For one thing, a person can print them out and write on them, for example, are available at the URL that I have there. So you could actually go right now and sort of look ahead kind of 4 or 5 levels and see if it suits where you want to be. Okay, and then the level. So again, somebody who's trying to decide whether this sequence of videos suits what they need is saying to themselves something like, I don't want it to be too hard. I also don't want it to be too easy. If the course is too hard and you never have any idea what's happening, not that you didn't learn anything from the course. If the course is too easy and you were stepped through stuff you already knew, you didn't learn anything either. So we're trying to hit that sort of happy medium that gets, again, something like 80 or 85% of most people at a mainstream U.S. college science or engineering program. So if you, for example, want to be an electrical engineer, if you want to be an economist, if you want to be a math major, if you want to be a computer science major, all those things would probably fall into a course such as this. In particular, one thing that folks are often worried on the first day of a Calculus 1 class is it going to be too hard for me? It says math at the beginning of the class. Is it going to be strictly focused on math? And the answer, perhaps to the disappointment of some people, but the answer is that we have a lot of audiences in the room. And so sometimes we will talk to the fine points of the mathematics, absolutely right, but more often we sort of aim for scientists in general, physicists, chemists, engineers, computer scientists, that kind of thing, sort of trying to make a broader stroke. Okay? Okay, so I hope this is what you're looking for. I hope this suits your needs. If so, then again, I'm going to take you to the first day's work, which is on the beginning of calculus. So let me bring up here full screen. Full screen. There we go. Have a little trouble manipulating the thing sometimes. So let's see. So I want to start by talking about the creation myth, a story that we all know. So we all know that during the plague of 1666, Newton's university shuts down, and has some resonance in all of our lives, I think. He goes to his aunt's farm in the country and has time to reflect, and specifically what he reflects about is the motion of heavenly bodies. And the story goes, the sight of an apple falling from the tree inspires him to hypothesize that the force pulling the apple to the earth is the same force that pulls the moon to the earth. He does the math, and that assumption proves to explain the orbit of the moon as well as the orbit of the planets around the sun. And then some years later, when Edmund Halley comes to ask him about Halley's Comet, Newton says, I have those calculations here somewhere. I'll find them. I'll send them to you. A lot of people seem not to know that tree, the tree in the story, actually still exists. There it is. You can go to visit it, and sometimes there are various universities that have like a seed from the tree, and they planted it, and they have a child of the tree in their sort of courtyard. Very nice. So when the story goes, when he received that work, Halley urged Newton to publish it. In fact, he paid for the publication, and Newton's work became a foundation for our modern age. So I think everybody knows the story. Everybody has seen sort of cartoon versions of Newton sitting in the garden, and an apple hits him on the head. Even Newton didn't claim the apple hit him on the head. And suddenly, he has this flash of insight. So it's a great story, a very good story. Unfortunately, it's not a true story. So people who study the history of the subject really don't think that there's all that much to it. And here's a very well-regarded history of science, very well-regarded. And I have a quote. I know you can read, but sometimes it helps me to pace myself if I talk my way through it. More than any other scientific myth, Newton's falling apple promotes the romantic notion that great geniuses make momentous discoveries suddenly and in isolation. And when Dr. Forrest says romantic notion, we're talking about the period of time, as well as the idea that it's somehow what would you say, dressed up, fancy, somehow like a fantasy. Although Newton was undoubtedly a brilliant man, eulogies to a lone genius, in fact, failed to match events. And just as an example, the person who suggested that the force that calls the apple to the earth is the same as the force that calls the moon to the earth was not Newton, that was Hooke. Like all innovators, he depended on the earlier work of Kepler, Galileo, Descartes, and countless others. So we'll be brief, but we want to give some closing background for the subject's origin, and the new story will be at least a little more true and include a little bit of context. And in particular, I talked a few minutes ago about having a number of audiences in the room. If you are a person who might someday teach the subject, I hope that you'll teach the version that's true, because truth is a gem. So we have to start somewhere. So I'm going to start with Tycho Brahe. So the correct prediction of the solar eclipse in 1560 so impressed Tycho Brahe that he dedicated his life to astronomy. Can you see, Tycho Brahe is born in 1546 and the eclipse is 1560, so he was that kind of impressionable age. He realized that what astronomy needed was systematic, rigorous observation, that is to say, data. Somebody had to go out there night after night after night and write this stuff down. He was fantastically wealthy. He had 1% of all the wealth in Denmark. And the king gave him an island, and he built large astronomical instruments on that island. He was, in fact, the last major astronomer to work without a telescope. So here's a drawing. Can you kind of see him here? There he is. And he's pointing to this little window there, and he's talking to his assistants. There are the assistants down here, and he's saying to the assistants something like, okay, we put that cat whisker across that little window, and we're going to tell you when Venus crosses the cat whisker, and it is right now. And they write down exactly the moment when the astronomical event happened. So they got piles and piles, books and books and books of data. Kepler was assisted by, Brahe was assisted by Kepler. Right? Kepler inherited Brahe's data and spent years analyzing. He synthesized the observation into the celebrated 3 laws. The orbit of every planet is an ellipse. The line segment between the planet and the sun sweeps out equal areas in equal times, and the square of the planet's orbital period is proportional to the cube of the semi-major axis of its orbit. Although these are laws in the sense that you could go out with a telescope and verify them, the situation was very unsatisfactory. The laws seem arbitrary. No one could explain why they held. I mean, just to start with the very first couple of words, why is the orbit of a planet an ellipse and not a circle? I mean, what's going on with the semi-major axis here? How come one of the axes is longer than the other one? Does this like point to some magic spot in the night sky? What's going on here? Why is it not a circle? Why is it not perfectly symmetrical? So it demanded explanation. And here are the 2 people who explained it. These 2 developed the basics of calculus at roughly the same time. And of course, already talked a little bit about Newton. He obtained his degree in 1665 from Trinity College, Cambridge, just before they closed because of the Great Plague. Over the next 2 years in the country, his private studies saw progress in calculus, optics, law of gravitation, and he eventually published his celebrated text. Leibniz there, the other fellow, what a wig, isn't that wonderful? He was a German mathematician, philosopher, and diplomat. In addition to his work on calculus, he made major contributions to physics, technology. He, in fact, made one of the earliest calculators. Philosophy, probability theory, biology, medicine, geology, psychology, linguistics, and information science. So I think most of the folks watching this video will have heard of Newton. I want to sort of pile on the accolades for Leibniz because he was also a genius. Not talking down Newton, but talking up Leibniz. Calculus can be derived from Kepler's laws from the single assumption that gravitational force follows the inverse square law. So here, of course, is the inverse square law. You see r squared on the bottom of the fraction. For example, if you consider the second law, the line segment connecting the planet with the sun sweeps out equal areas in equal times. I took what's the motion of the planet there, and I marked it off into 1 month, 2 months, 3 months, like that. You see the planet. You draw a line connecting the planet to the sun, and that line sweeps out an area in a month. Now, to derive this law from the inverse square law, Leibniz and Newton needed to overcome 2 technical points. First point, you can see that far from the sun, the planet moves not all that far in a month, but near to the sun, the planet moves quite the distance in a month. So the planet is moving at different speeds at different times of its orbit. So they have to be able to compute the speed of the planet. Second, how do you compute the area of these oddball regions? Let me just pick one this one right here. That's not really a triangle. This side right here, for example, is not square. It's not flat. It's curved. So it's not quite a triangle. How do you compute the area of those odd-shaped regions? So again, the first great problem of calculus is to find rates of change. You have to find the velocity of a planet in its orbit as the rate of change of its position. In this course, we'll spend most of our time on this problem. Maybe 2/3 of the course, maybe 3/4 of the course, being able to solve the problem of rates of change. Calculus's other great problem, so what's left in the course, 1/3 or 1/4 of the course, calculus's other great problem is the accumulation problem. Kepler's second law says that planets sweep out equal areas in equal times, so I drew a planet sweeping out an area in 10 days, we can't just add those little slices to accumulate the total area, because what's being swept out changes from instant to instant. So every slice is different shaped, and there's infinitely many instants. At the end of the course, we're going to study the accumulation of continuous quantities. So again, maybe the last third, maybe the last quarter. Sometimes this is called the area problem, because solving it lets us find areas. So the two great problems of calculus are rates of change and the area problem, the accumulation problem. So to wrap it up, over the intervening time, calculus has been developed and extended to just a tremendous extent. It's an extremely powerful tool at this point. It has many, many applications, and indeed entire fields think largely in calculus. Even today, development continues at a great pace, although if you were a present-day researcher, a sort of descendant of Newton and Leibniz, you probably wouldn't say I'm a calculuser. You probably say something like I'm an analyst, or you might say some other subject, topologist, for example. But nonetheless, this is the research that has come out of the early work, the research that has come out of the things that we will consider over the course of the semester. Okay, I hope you stick around for the other videos that we have, and nice to have you aboard.